Okay, so we have a plasma physics semester one practice final exam at the graduate level in physics. So let's get right into it. I'll try to go through this relatively quickly. You have the setups and answers as a reference. Okay, sorry if I talk too fast or miscommunicate anywhere. So let's start. Number one, a hydrogen plasma electron temperature, T sub E equals 80 and density N sub E is 4 times 10 to the 17th per cubic meter. Okay, part A. Okay, so we have compute the electron debye length. Okay, debye. Electron debye length here. Formula, what we're going to do, we have lambda sub d equals square root of quantity epsilon naught k sub b t sub e over n sub e squared. Okay, so we're given that T sub e, that's the electron temperature, is 8 eV, and K sub b, T sub e is just 8e. So our lambda sub d is going to be epsilon naught times 8e over n sub e squared. Right here we get square root of e sub naught times 8, epsilon sub naught times 8, pardon me, over n sub e times e. We're going to be using n sub e as given is 4 times 10 to the 17th. And here, lambda sub d, that's going to be approximately 3.32 times 10 to the negative fifth. Lambda sub d is approximately 33.2. Okay, part B, particles in the debye sphere, n sub d, that's 4/3 pi, n sub e lambda cubed, lambda sub d cubed, my apologies. So n sub d is approximately 4/3 times the quantity 4 times 10 to the 17th times the quantity 3.32 times 10 to the negative fifth cubed. N sub d is approximately 6.16 times 10 to the fourth. Okay, moving forward here, our plasma approximation. Okay, so our plasma approximation is valid when N sub d is much greater than 1. So let's see what we can do here. So assuming, well, we have N sub d is 6.16 times 10 to the fourth. That is a value much greater than 1. So is the plasma approximation valid? Yes, the plasma approximation is valid for this. And part D, suppose the density decreases by a factor of 100 while temperature remains fixed. Explain qualitatively and quantitatively how the debye length changes. Okay, so for letter D, the density decreases by a factor of 100. And since right here we have this proportional relationship, the lambda sub d is proportional to 1 over square root of n sub e. What we could say here is if the density decreases by a factor of 100, lambda sub d, what we have here is that's going to be now going to 10 lambda sub d. So lambda sub d will be 3.32 times 10 to the negative fourth m. Okay, so we have that debye length becomes about 332 here in micrometers, and that's all for A, B, C, or D. Pardon me if I misspeak or mislabel anything, talk too quickly during this. I did go through this a bit too quickly when I did the exam, but anyway, it should be all right. Moving along, number 2, but always, again, never trust, always verify. Human error, human input error, user error is a real thing, and I'm guilty of that a lot, making a lot of mistakes, small mistakes, and sometimes I don't get my corrections, but this is pretty solid overall, so don't worry. It's just that if I misspeak or if I mislabeled something, my apologies. But then again, this is solid, even though it's plasma. Haha, little humor. Okay, number 2. Consider a cold, collisionless electron plasma with fixed ion background. Okay, so that's our situation. Part A, starting from the electron fluid equation and Poisson's equation, derive the electron plasma frequency. Okie dokie. So this here we have this is plasma oscillations type problem. So our derivation, this is more textbook based. So for cold electrons, m sub e, and we have that second derivative, x with respect to t, that equals negative e times capital E, so that's the electron charge times the first order electron field, times the first order electron field perturbation. If electrons are displaced by x, a charge imbalance appears. So let's see what we have. We've rho is n sub e ex. So using Poisson's equation, we have this right here. This del operator dotted with E, okay, and that equals our right side. For the slab displacement argument, we have E equals n sub E Ex over epsilon naught, and we're going to substitute that into our equation of motion, which is right here. Substitute, and then we're going to set it equal to 0. And then what we're going to do is we're going to isolate, and we're going to get our omega sub PE. That's going to equal the square root of n sub e squared over epsilon m sub e. Okay, so that's part A. For part B, plasma frequency, calculate the plasma frequency for n sub e equals 2 times 10 to the 18th. Per meter cubed. So let's see here. We're given that. We're going to use the formula here, W sub PE. We're just going to substitute our values. And then this gets converted to radians per second. So it's 7.98 times 10 to the 10th radians per second. And if you want to add to this the ordinary frequency, that's what we're looking for. But also the ordinary frequency, F equals omega over 2 pi. That would be 1.27 times 10 to the 10th hertz if we are to substitute the value in for omega. All right, so that's part B. Part C, suppose the electrons are displaced by the function x of t equals x naught cosine of omega t. Find the associated electric field as a function of displacement. So here, electric field is a function of displacement, so we have our electric field equals n sub e over epsilon naught x and times x rather. The field points in a restoring direction for the electron motion. So here's what we have. If we're given this function here, then E of t equals n sub e x naught over epsilon naught times cosine of omega t. Okay, so that should look very familiar. Think about where that came from. Now, the direction is determined by the displacement geometry. Okay. And I apologize if I misspoke here in any way. I did not have enough coffee today, so if I misspeak, my apologies, but the math and the setups, I'm almost 100% sure for this, are all correct. Part D, explain physically why plasma oscillations do not propagate in the cold electrostatic limit. And also the explanations are good. Okay, so at least they very well should be. D, our answer is cold electrostatic plasma oscillations do not propagate. In the cold limit, we have the dispersion relation is here omega equals omega sub PE. It does not depend on K. Therefore, V sub G equals d omega over dk equals 0. So there is no group velocity. And called Langmuir oscillations are local oscillations and are not propagating waves. Okay, so that's for number 2. We're ready to go on to number 3. Again, I'm just trying to get you through this so you have this as a reference. Okay, so. All right, so here we have a proton. So for number 3, we have a proton enters a uniform magnetic field. Here's our magnetic field, 0.20 z hat t. With velocity given here, 3 times 10 to the 5th x hat plus 4 times 10 to the 5th z hat meters per second. Okay. All right, so this is straightforward here. Find the cyclotron velocity for letter A. So this is charged particle motion. We take what we're given. Okay, and in this situation, V sub perpendicular is 3 times 10 to the 5th. V sub parallel is 4 plus 10 to the 5th. So cyclotron frequency for a proton. Please forgive my horribly illustrated omegas. Omega sub c is EB over M sub P. Substitute our values in and 1.60 times 10 to the negative 19th for E, or magnetic field 0.20 over 1.67 times 10 to the negative 27th for M sub P. We're going to get our omega sub c is approximately 1.92 times 10 to the 7th radians per second. That's our cyclotron velocity. Okay, part B, we want to determine the Larmor radius. So Larmor radius, we're going to use R sub L equals MP, M sub P times V sub perpendicular over EB. And we're just going to substitute our values, and we're going to get R sub L is 1.57 centimeters. Pitch angle, determine the pitch angle for letter C. Well, to do that, we're going to take the tangent ratio of V sub perpendicular over V sub parallel. That's going to give us 0.75. Take the inverse tan there. We get theta is approximately 36.9 degrees for the pitch angle. Part D, write parametric equations for the particle trajectory. So parametric trajectory for the positive charge is going to be the magnetic field equals B times Z hat. And in this situation, X of t equals R sub L, okay, our Larmor radius there, times sine of omega sub c t, and then Y of t equals R sub L, cosine of omega sub c t. Now, this is up to the phase convention, and our Z of t is V parallel to t. So one acceptable form is these 3 equations here. X of t is RL sine of omega sub t times c, omega sub c times t rather. Y of t equals R sub L cosine of omega sub c t, and then Z of t equals 4 times 10 to the 5th t, because that's our V sub parallel t. And these heliacal trajectories, the phase choices are arbitrary, so this is an acceptable answer. And just here, R sub L is 1.57 times 10 to the negative 2. M and our omega sub c, that's 1.92 times 10 to the 7th radians per second. Okay, so moving, and that was from the previous, that was from A and B. And letter E, let's see here, explain how the trajectory changes if a uniform electric field E equals 1500 Y hat V over M is added. So here we go, adding an electric field. Here's what we're given. So what we want to do, cross product of E and B, the electric field and the magnetic field, the drift. The E cross B drift is going to be V sub E, okay, so V sub E is the cross product of E and B over B squared. And here's the nice thing, the cross product of E and B that's just going to be Y hat cross Z hat. That yields X hat. So V sub E is going to be E over B X hat. And V sub E is going to be 1500, which we were given. So we were given the 1500 over what we're given here for our B, 0.20. So we're going to get V sub B is 7.5 times 10 to the third, X hat meters per second. So what we could say here is the proton still gyrates, however its guiding center drifts, in the positive X hat direction. So that's all for number 3. Moving on to number 4. Whoops. Sorry. Okay, number 4. Okay, so number 4, we have consider a plasma in fields. Magnetic field equals B naught Z hat. Electric equals E naught X hat. So for part A, we want to derive the E cross B drift velocity. So the drifts, E cross B drift for uniform fields, the drift velocity is V sub E equals E cross B over B squared. We're given E equals E naught X hat, B equals B naught Z hat. E cross B equals E naught V naught times the quantity crossing X hat and Z hat. So you're going to wind up with negative E naught, B naught, Y hat. So V sub E equals negative E naught over B naught, Y hat. Okay, so from here, let's see what we have. Part B. Show explicitly that the drift is independent of particle charge and mass. Okay, so this is what we could say for independence from charge and mass. V sub E cross product E and B over B squared contains neither Q nor M. Therefore, electrons and ions drift together. E cross B drift causes no charge separation by itself. Okay, moving along to letter C. Now suppose the magnetic field varies as B of Y equals B naught times the quantity 1 plus that's 1 plus alpha y. And we want to derive the grad B drift velocity for ions. So, grad B drift, we're going to use this. Grad B drift is that velocity sub del operator B. That equals this whole thing, mv perpendicular squared over 2qb cubed times the magnetic field. And that's going to be crossed with our del operator of B. Okay, so here what we're going to wind up with, B of Y is B naught times the quantity 1 plus, right here, this alpha Y. So our del operator of B is going to be, that's dB dy y hat. That's going to equal alpha B naught y hat, and our B cross del B, that's going to be B naught Z hat crossed with alpha B naught Y hat. So that's going to yield negative alpha B naught squared X hat. Okay, so from here, we could say our V sub delta B here, that's going to be mv perpendicular squared over 2q b cubed b naught cubed times quantity negative alpha b naught squared x hat. So this is going to come out to here negative m v perpendicular squared alpha over 2q b naught x hat. And for ions, we get q as positive E. So what we could say here is for our gradient here, our grade B drift, okay, velocity in ions, we're going to wind up with negative m sub I v squared, v perpendicular squared I, alpha over 2e b naught x hat. Here is our answer, and pardon me if I used an incorrect notation somewhere in C. This is the correct answer. I was writing a few things too fast, but this is right here. This is correct. This is our grad B drift on the right-hand side. That's correct. Made a little miscommunication. Happens writing too fast. My apologies. So letter D, electron and ion directions. So for electrons and ions, determine the relative directions of the grad B drift. So for ions, Q equals plus E. So the drift is in the negative x hat direction if alpha is greater than 0. For electrons, Q equals negative E. So the drift reverses and is in the positive x hat direction. So what we could say here is ion and electron grad B drifts, they're opposites. So that takes care of, that would be letter D. And now we could do letter E. And just going back to what letter E wanted, letter E right here, explain how these drifts contribute to charge separation in magnetized plasmas. So what we have here for letter E, we could say charge separation because the grad B drift depends on 1 over Q. Ions and electrons drift in opposite directions. This separates charge and can produce currents. And by contrast, the cross product of E and B drift does not separate charge because both species drift together. Okay, so that's all for number 4. Let's move along to number 5. Whoops, sorry about that. Again, I should probably have had more coffee before presenting, but so be it. Number 5, cylindrical plasma column of radius A, so radius A, carries axial current density. So here we have J sub Z of R equals J naught times the quantity 1 minus R squared over A squared. So we're dealing with current density here. So A, using Ampere's law, determine the azimuthal magnetic field B sub theta of R inside the plasma. Okay, so using our MHD equilibrium, this is an MHD equilibrium problem. So given our J sub Z of R, okay, magnet field, we're going to use Ampere's law. All right, there's Ampere's law. And luckily for cylindrical symmetry, B sub theta, this is of 2 pi r, that equals that mu naught I sub ENC of R, okay? And the enclosed current, I sub ENC of R, is going to equal this integral 0 to R, J sub Z, R prime, 2 pi R prime, D R prime. Okay, now, just moving along, when we perform integration, I didn't write out all the steps for this, for the computation algebra portion. We're going to wind up with B sub theta of R. That's going to be mu naught J naught times the quantity R over 2 minus R cubed over 4A squared. Okay, so we have these two, and that is our B sub theta of R. Okay, so we have part A. Let's move on to part B. So just using this as a reference, here's B, C, and D. We'll just if you're doing these as along, well, you could always scroll back. I'm going to say it anyway, what we're doing. Okay, so for part B, starting from MHD equilibrium condition, here's what we're given. That del operator there equals the J cross B. So here we go. J cross B. Okay, so sorry about that. And this is for pressure. Sometimes I visually have some issues distinguishing rho from the pressure. It happens at times, especially if I'm not wearing my glasses. I have to remind myself we're not dealing with rho here. Okay, we're not dealing with momentum, we're dealing with pressure. Okay, happens all the time. Just like sometimes electrons, if I'm doing a lot of mathematics, I have to remember E, talking about electrons here, and then sometimes E, I think of Euler's number. It happens. So many letters. So here are symbols that look alike. Pressure profile, MHD equilibrium. We have that cross product JB. So here J is J sub Z, Z hat. B equals B sub theta, theta hat. Now here's where it gets interesting. Since Z hat cross theta hat equals negative R hat, if we get this derivative, we take the derivative of the dpdr, that's going to be negative J sub Z B sub theta. Now, if we do some substitution here from what we have before, dpdr, that's negative J naught times the quantity 1 minus R squared over A squared, mu naught, J naught times the quantity R over 2 minus R cubed over 4A squared. Okay, so just putting these figures together here, just rewriting it. Now using P of A equals 0, P of R from R to A, that's going to be J sub Z, R prime, B sub theta, R prime, D R prime. So, performing the integration, I didn't show the steps in between with the computation, but if you integrate, you get P of R is mu naught J naught squared times this. I'll just read it out. This quantity inside the brackets, 5A squared over 48 minus R squared over 4, plus 3R to the 4th over 16A squared minus R to the 6th over 24A to the 4th. Okay, so that takes care of part B. Part C, what they were asking is determine whether pressure increases or decreases toward the center. So, does pressure increase towards the center? So here's what we could say. At R equals A, P of A equals 0. And at R equals 0, P of 0 equals U naught J naught squared times 5A squared over 48. Okay? And that's from here. So pressure is largest at the center. As we go further and further towards the center, pressure increases towards the center. Okay. Part D, what they want is explain physically the origin of magnetic confinement in this configuration. So the physical origin of the confinement, and what we could say is this: the axial current produces an azimuthal magnetic field. The force cross product of J and B points inward, balancing the outward pressure gradient. And this is magnetic pinch confinement. And we could say the plasma is confined by the inward pinch force. Okay, so that's part D of number 5, and then we are ready to go into number 6. Okay, number 6. Let's see. Okay, we're good. 6. Consider a fully ionized hydrogen plasma in equilibrium magnetic field where B naught equals B naught Z hat, starting from the ideal MHD equations. Okay, derive the Alfvén wave dispersion relations show. So this technically, we're dealing with the Alfvén waves. Dispersion relation here, the ideal MHD momentum equation. Here we have rho naught. This time it's rho, not P, not pressure. Now we're dealing with momentum. Aha. Rho naught, and we have a partial here, derivative of V, T, V sub 1 with respect to T equals 1 over mu naught times the del operator crossed with B sub 1, in parentheses, crossed with B naught. So we could say the induction equation is that partial derivative, dB sub 1 dt equals the del operator crossed with the cross product of V sub 1 and B naught. Okay, so here's what we're going to do. Here we're going to assume the perturbations are of the form e to the I kz minus wt with B naught equals B naught z hat. So going up here, the induction equation gives negative omega B sub 1 equals I k B naught V sub 1. So B sub 1 equals negative k B naught omega B sub 1. The momentum equation gives us the following: negative I omega rho naught V sub 1 equals I k B naught over mu naught B sub 1. We're going to substitute our B sub 1. So we're going to have omega squared P naught, omega squared rho naught, V sub 1 equals k squared B naught squared over mu naught times V sub 1. So omega squared equals k squared B naught squared over mu naught rho naught. And our omega is going to be k V sub A, where V sub A equals B naught over the square root of the product of mu naught and rho naught. Okay, so that was an interesting one with the dispersion relation. Part B, show that the perturbation is transverse. Okay, transverse nature. Okay, for shear Alfvén waves, K is parallel to B naught, and the perturbation velocity is going to satisfy the V sub 1 perpendicular to B naught. So also B sub 1 is perpendicular to B naught. Therefore, the wave is transverse for V sub 1. B sub 1 is perpendicular to B sub naught. Okay, for part C, compute the Alfvén speed given B naught equals 0.35 t, and n sub 1 is 5 times 10 to the 18th m to the negative 3. So for hydrogen, our rho naught equals n sub I m sub p. So what we're going to have here is rho naught equals, that's 5 times 10 to the 18th times the quantity 1.67 times 10 to the negative 27th. Think about where those come from. And from here, rho naught, that's going to be 8.35 times 10 to the negative 9 kg over m cubed. So since VA, right, VA is here, that's substituting for the numerator, we're going to get 0.35 over that square root of mu naught rho naught product, and we're going to get for V sub A is approximately 3.41 times 10 to the 6 meters per second, and that's for letter C. Okay, now we have letters D and E. So letter D, let's just read it here. A wave has wavelength 0.80 meters. Determine its angular frequency. Okay, so angular frequency here. So our lambda is 0.80 meters, and our k value is 2 pi over lambda. So we're just going to take 2 pi divided by 0.80. That's going to be 7.85 m negative 1, and our omega is k V sub A. Substituting here, W is just, omega is 7.85 times the quantity 3.41 times 10 to the 6th. So our omega is approximately 2.68 times 10 to the 7th radians per second for number 6. 6D rather. 6E, it's telling us discuss one major limitation of ideal MHD in describing high frequency plasma waves. So here's what we can say. A limitation of ideal MHD. Ideal MHD assumes that our omega is much less than, our omega is much less than this capitalized omega sub I. So what we have here in the length assumes that the length scale is much larger than the kinetic scales, such as the ion gyro radius and Debye length. So the ideal MHD cannot accurately describe the high frequency waves such as Langmuir waves, electron, cyclotron waves, or kinetic damping effects. Okay, and I apologize for my very poor symbol drawing there. Okay, so I apologize if I misspoke anywhere, but the math looks all right. Setups look all right for number 6. Let's move along to number 7, Langmuir waves problem. Okay. Okie dokie. All right. So, number 7, consider small electrostatic perturbations in a warm electron plasma. Part A, use the linearized fluid equations and Poisson's equation. Derive the Baum-Gross dispersion relation, omega squared equals then omega sub PE squared plus 3K squared. And then we have our V sub TH squared. All right, so let's see here, and that being that threshold velocity here. All right, okay, we're good. Langmuir waves. Okay, so for part A, what we want to do, Baum-Gross dispersion relation, the warm electron fluid equations are we need for continuity and momentum. Here they are respectively. For continuity and momentum, we have the partial derivative here, dn sub 1 dt plus n naught and del operator dotted with v sub 1 equals 0 for continuity. And for momentum, m sub e, partial derivative v sub 1 with respect to t equals negative e sub 1 minus 1 over n naught, del operator, that p sub 1. Okay, so here, going back to pressure, before it was momentum, now going back to pressure here. So for adiabatic one-dimensional electron pressure, p sub 1 equals 3k sub b, t sub b, n sub 1. And I apologize again just from reading this too fast if I read something as pressure that's momentum and momentum as pressure because of the P-like shape for rho. My apologies, but the math is correct. My apologies. So here we have for our adiabatic one-dimensional electron pressure, and then Poisson's equation we have here. So what we're going to do here, assume plane waves, so e to the I, parentheses kx minus wt, and that should be I written formally, not in print. So continuity gives the following: negative omega n sub 1 plus k, n naught v sub 1 equals 0, and then that n sub 1 equals k n naught over omega v sub 1. Now momentum is going to give the following: negative I omega m sub e v sub 1, that's going to equal negative e sub 1 minus ik over n naught, 3 k sub b t sub e n sub 1. Okay, so moving along to the next portion, almost done with part A. So moving along Okay, so sorry about that. So part 7a continued here. What we have here is combining with Poisson's equation is going to give us the following, that omega squared equals omega sub Pe squared plus 3k squared V sub Th squared, where V sub Th squared equals K sub B T sub E over M sub E. Okay, so we derive the Baum-Gross dispersion relation. Okay, so right there, that W squared, that omega squared, that's what we were looking for there. The dispersion relation, Baum-Gross. So, part B. Part B, they want us to explain the physical origin of the thermal correction term. Okay, so let's see here. Part B, physical meaning. The term omega sub Pe squared comes from electrostatic charge separation. The term 3k squared V sub Th squared comes from thermal pressure. Electron pressure adds an additional restoring force. So warm Langmuir waves oscillate slightly faster than cold plasma oscillations. Okay. That's for part B. For part C, let's see what they want here for C. Okay, so for C, if you go back, I'm just going to read it out. For the N sub E is 10 to the 18th, M negative 3, T sub E is 12 eV, and K equals 120 negative 1. That's what they gave us. And they want us to compute the wave frequency here. So want us to compute wave frequency, so numerical frequency here. We're going to use W sub Pe equals that square root of Ne E squared over epsilon naught M sub E. W sub Pe is approximately 5.64 times 10 to the 10th radians per second. And we have our thermal speed, V sub Th. Okay, if we take the square root here, from here, that's square root of K sub B, Te over M sub E. So that's thermal speed is going to be 1.45 times 10 to the 6th meters per second when we substitute values. So then our omega is square root of omega sub Pe squared plus 3k squared V sub Th squared. So our omega is 5.641 times 10 to the 10th radians per second. And the ordinary frequency is going to be 8.98 times 10 to the 9th hertz. Moving along into part D. Part D, what they want is determine the phase velocity and compare it with the electron thermal velocity. Okay, interesting one. So phase velocity, V sub phi equals omega over K. So V sub phi equals 5.641 times 10 to the 10th over 120 when it's one substituting. So our V sub phi is 4.70 times 10 to the 8th meters per second. So what we're going to do is we're going to compare this with V sub Th, which is 1.45 times 10 to the 6th seconds, meters per second rather. And if we have a ratio here, if we make a ratio V sub phi over V sub Th, that gives you 324. So a ratio of about 324 to 1. So V sub phi is much, much larger than V sub Th. So what we could say here, and this is interesting because it's a little counterintuitive, this is greater than C. Think about which signals that the chosen K is in the very long wavelength electrostatic limit, and the phase velocity is not a signal speed. Also, the chosen K gives a weak Landau damping. So what we could say here, just going off to the right, the model is non-relativistic. And our phase velocity does not carry information. Okay, so moving along to letter E. Letter E, under what conditions would Landau damping become important? Okay, so Landau damping. So Landau damping becomes important when the phase velocity is comparable to the velocity of many particles. So this would be when v sub phi is approximately v sub th. However, in this situation, our v sub phi is much, much larger than v sub th. So we can conclude the Landau damping would be weak. So it becomes stronger for a larger k because v sub phi would equal omega over k. It decreases as k increases. Okay, so that's for part E, and that's for number 7. So moving along to number 8. Okay, so number 8, let's see what we can do here. Okay. So number 8, consider a quasi-neutral plasma consisting of electrons and singly ionized ions. Part A, write down the continuity and momentum equations for each species. So this is more textbook. We have a 2-fluid plasma dynamic problem here. So 2 fluid equations for species. S, we get this partial derivative, this n sub s over d n sub s over dt partial plus our del operator dotted with n sub s v sub s, that equals 0. And our momentum equation, I'm not going to read it for sake of brevity, that's this whole thing. And this is textbook. These are textbook equations. And canonical, for ions, Q sub I equals positive E, and for electrons, Q sub E equals negative V. So that's what we do. Write down our equations we need. Textbook, canonical. Part B, starting from the 2 fluid equations, derive the ion acoustic wave dispersion relation in the limit T sub E is much larger than T sub I. Okay, fun one. So, for part B, ion acoustic dispersion relation. So we're for ion acoustic waves, assume T sub E is much, much larger than T sub I. Electrons are light and respond approximately to Boltzmann, where you have n sub E equals n sub and not exponential of E phi over k sub B T sub E. Okay, now going up here, right here, for small phi, n sub E approximates this. N sub E approximates n naught times the quantity 1 plus E phi over k sub B T sub E. Now from here, so n sub E1 equals n naught E phi over k sub B T sub E. T sub E. And quasi-neutrality gives this n sub I1 approximately n sub E1. Okay, so from here, dealing with these perturbed electron densities, ion continuity, we take the derivative here, that dn sub I1 dt partial plus n naught partial d v sub I dx partial equals 0. So in ion momentum, m sub I, take this partial, d v sub I over dt, that equals negative v d phi over dx. Again, we're going to assume plane waves, so e to the I, parentheses kx minus omega t. So when we come up here for our continuity, what we're saying here is our negative omega n sub I1 plus k n naught v sub I equals 0. And for our momentum, negative, so here was the continuity. Now we go to momentum. The momentum is negative negative omega m sub I v sub I equals negative k e phi. So v sub I equals k e phi over m sub I omega. And now what we're going to do, we're going to substitute into the continuity. So n sub I1 equals k n naught over omega times the quantity k e phi over m sub I omega. So here n sub I1 equals k squared n naught e omega over m sub I omega squared. Okay. Now, however, quasi-neutrality gives us this. N sub I1 equals n naught times E phi over K sub B T sub B. And what we're going to do is we're going to equate. Let me just move along. Second page here. Set up a proportion. We're going to equate here. N sub I1 equals N sub I1. So this is going to be K squared N naught E phi equals N naught E phi over M sub I. And I'm sorry, let me do the left-hand side first. K squared N naught E phi over M sub I omega squared equals, right-hand side, N naught E phi over K sub B T sub B. Okay, simplifying here, we get K squared over Mi omega squared equals 1 over K sub B T sub B. Omega squared is K squared K sub B T sub B over N sub I. So our omega is going to be K C sub S. And C sub S is going to equal the square root of K sub B T sub B over N M sub I. Okay, so that takes care of that portion. That was part B. Okay. So that the ion acoustic wave dispersion relation. Okay. In relation to the limit T sub B much greater than T sub I. Now to part C, we want to determine the ion acoustic speed. So right here, ion acoustic speed for cold ions in isothermal reactions, C sub S equals what we derived here, K square root of K sub B, T sub B over M sub I. And if the ion temperature is included more carefully, C sub S is going to be square root of K sub B T sub B plus, sorry, that's a gamma sub I, K sub B, T sub I over M sub I. So, and this is for one-dimensional adiabatic ions, often when gamma sub I equals 3. Okay. Part D. What it's saying is for a plasma with T sub E equals 15 eV and T sub I equals 0.5 eV, calculate the ion acoustic speed. Okay, so here's what we were given. T sub E is 15 eV and T sub I is 0.5 eV. Using the cold ion approximation, C sub S, that would be now square root of 15e over m sub p. So C sub S is approximately 3.79 times 10 to the 4th meters per second. Now with the T sub I, and with gamma sub I equals 3 and T sub I equals 0.5 eV, C sub 3 would be the square root of quantity 15 plus 3 times 0.5 in brackets times E over M sub P, and they're going to take the square root of that. When substituting, this is going to become C sub S is approximately, substituting and reducing, and performing the computation, C sub S is approximately 3.97 times 10 to the 4th meters per second. So, what we could say is, so either value is acceptable depending on the approximation, but the cold ion result is the intended one. Okay. And then part E, Part E, what they want us to do is they want us to explain physically why ion acoustic waves disappear when T sub I approximates T sub E. Okay, interesting here. So, why waves disappear when T sub I approximates T sub E. So, ion acoustic waves require electrons to provide pressure, restoring force, while ions provide inertia. So for weak damping, the phase speed should satisfy approximately this. This V sub Thi is going to be much less than V sub phi, which is much less than V sub The. So when T sub I is approximately T sub E, we could say the ion thermal speed becomes comparable to the ion acoustic speed, and many ions resonate with the wave, causing strong ion Landau damping. So right here, ion acoustic waves become strongly damped when T sub I approximates T sub E. Okay, so that's all for number 8, and now we can move on to number 9. So, number 9. All right, so for number 9, we have here a charged particle moves into a magnetic mirror configuration where the magnetic field increases from B sub 1 equals 0.25 T to B sub 2 equals 1.20 T. Okay, part A, using conservation of magnetic moment, derive the mirror condition. All right, so magnetic mirror problem. Take what we're given for B sub 1 and B sub 2. Mirror condition, magnetic moment is conserved. When we have mu equals that m v perpendicular squared over 2b. And at the weak field region, mu is mv squared sine squared theta sub 1 over 2b sub 1. Now at the mirror point, v sub parallel equals 0, and v sub perpendicular is v sub 1. So our mu equals mv squared over 2b sub 2. Set up a proportion here. Mv squared sine squared theta sub 1 over 2 b sub 1. That equals mv squared over 2b sub 2. Our sine squared theta equals b sub 1 over b sub 2. So what this would mean, so the reflection would require the inequality in this situation, sine squared theta sub 1 is greater than or equal to ratio b sub 1 over b sub 2. So that takes care of letter A. Letter B, determine the minimum initial pitch angle required for reflection. So the minimum pitch angle, sine squared theta sub min, all that's going to be, and using that formula, it's just going to be 0.25 over 1.20. It's just what we had here, right? For our sine squared theta sub 1. So substituting what we have for b sub 1 and b sub 2, and we wind up with, when we solve for that equation, we get the angle approximates 27.2 degrees for the pitch angle, and that's all for letter B. And for letter C, suppose the particle initially has speed v equals 2.5 times 10 to the 6 meters per second. Find the parallel velocity at the weak field region corresponding to marginal trapping. So what we could say here, parallel velocity at marginal trapping. At marginal trapping, sine squared theta equals this ratio, b sub 1 over b sub 2. So cosine squared theta is going to be 1 minus b sub 1 over b2. V sub parallel is v cosine theta. Substituting, we're going to v sub parallel equals v times the quantity square root of 1 minus b sub 1 over b sub 2. So v sub parallel is going to be substituting 2.5 times 10 to the 6th times the square root of 1 minus 0.25 over 1.20. So v sub parallel velocity is approximately 2.22 times 10 to the 6th meters per second. So that takes care of letter C. Moving along to letter D. Letter D, they want us to explain the physical origin of the magnetic mirroring. So for letter D, see what we can do here. Okay, so physical origin of magnetic mirroring. So we could say as the particle moves into a stronger magnetic field, conservation of magnetic moment requires V sub perpendicular squared over B be equal to a constant. So V sub perpendicular increases as B increases. If total kinetic energy is conserved, the V sub parallel must decrease. At the mirror point, V sub parallel equals 0, and the particle reflects. Okay, and for letter E, what they wanted for letter E is discuss one major instability associated with mirror confinement systems. Okay, so mirror instability, what we could say, is one important instability is the mirror instability, which occurs when pressure is perpendicular to the magnetic field exceeds parallel pressure significantly. So when the pressure perpendicular is greater than the pressure parallel, and sufficiently. Now, more precisely, the mirror instability can occur when this happens, when the pressure here perpendicular over pressure parallel minus 1 is approximately greater than or equal to approximately 1 over that B or beta sub perpendicular. This produces growing magnetic field compressions and rarefactions. Okay, so that takes care of letter E, and that takes care of number 9, and now we go into our explanation one for number 10. Okay, number 10 is more conceptual textbook notes type stuff, canonical. So let's get into number 10. Number 10, plasma, instabilities and conceptual analysis. So for letter A, explain the physical difference between electrostatic and electromagnetic plasma waves. Okay, so here for letter A, what we could say, electrostatic waves have electric field perturbations mostly parallel to the wave vector, E sub 1 parallel to K. They involve charge separation and are often described using Poisson's equations. Examples include Langmuir waves and ion acoustic waves. Electromagnetic waves have coupled electric and magnetic perturbations, E sub 1 perpendicular to B, perpendicular to K. Examples include light waves in plasma, Alfvén waves, and Whistler waves. Okay, so that's letter A. Letter B, why are plasmas often called collective media? Part B, plasmas are collective because each charged particle interacts not only with nearby particles, but also with long-range electromagnetic fields generated by many particles. Okay, the Debye shielding limits the range of electrostatic fields, but within a Debye sphere, there are many particles, where you have n sub d is much larger than 1. So the behavior is collective rather than dominated by isolated two-particle collisions. Moving along to letter C, discuss the origin of the kink instability in current-carrying plasmas. So for letter C, a current-carrying plasma column produces an azimuthal magnetic field. If the plasma column is displaced sideways, the magnetic pressure and tension forces can amplify the displacement. The kink instability is especially associated with the mode number m equals 1. It causes the plasma column to bend like a kinked hose. Physically, too much axial current can make the plasma column macroscopically unstable. So that takes care of C. D, explain why collisions are often negligible in high temperature fusion plasmas. Okay, so for letter D, we could say Coulomb collision frequency decreases strongly with temperature. Roughly, we have that nu is proportional to n over t to the 3/2. So what we have here, as the temperature becomes very large, collision rates fall. We have here fusion plasmas are often high temperature and relatively low density compared with solids. So particles complete many gyro orbits or collective oscillations before suffering significant binary collisions. Thus, many fusion plasmas are approximately collisionless. We could add this. Also, the mean free path becomes much larger than characteristic system scales. Okay. Pardon me if I mispronounced anything. In part E, a plasma has plasma parameter. Here's what we're given. Explain whether fluid or kinetic descriptions are more important. So, we're given here lambda as defined as lambda sub d cubed is approximately 2. So let's see what we can do here. So the plasma parameter is, so lambda here in this, I'm just gonna, I already read it out. So if this lambda happens to be equal to this n lambda d cubed, a good plasma usually requires this lambda to be much greater than 1. However, here this lambda is approximately 2. This is not much larger than 1. Okay, thinking in orders of magnitude. So therefore, there are only a few particles in a Debye volume. Collective behavior is weak, and discreteness effects are important. Okay? A simple fluid description is questionable. A kinetic or particle-based description would be more appropriate, especially if one needs accurate treatment of fluctuations, shielding, or correlations. So lambda approximating 2 is marginal and not an ideal plasma limit. Okay, so that's all. 10 free response for this. My apologies, I didn't drink enough coffee today. It wasn't caffeinated enough. And my apologies if I mispronounced anything or wrote something down incorrectly. The overwhelming majority of this should be solid. I hope this helps anyone who wants to review plasma physics. And hopefully this could help as extra practice for an exam. Again, thank you very much, and have a great day.